Hello. Yes. We welcome you back to PSSB, Physical Sciences. Silver bullet with me, Richard here. Yes, today we are looking at this question. It comes from electrochemistry. And the statement says that consider the Daniel galvanic cell below. So this is it. What we call Daniel cell is the cell between copper and zinc. And this is the setup we are having. And then the question comes, write half cell reaction at cathode. Okay. How do we start with this? What do we do? Where do you look? In this case, the most important aspect is to find out which one is cathode and which one is anode. Before you proceed, that's the most important aspect. You need to identify which one is cathode and which one is anode. Okay, to do that, we use the table 4B. To me is the most suitable one. With the table 4B, you have to remember that what you have at the top are strong reducing agents, and what you have at the bottom are strong oxidizing agents. And we are looking at two elements under comparison here. We are looking at copper and we are looking at zinc. So in this case, the copper is here. Yes, that's the copper we are having. And zinc is here. So what do we notice? Zinc comes before copper. So in other words, zinc is a strong reducing agent compared to copper. So this is what now we have to know. That when you look at our table, which we call table 4B, it is zinc which is here and copper which is here. And we said zinc is a strong reducing agent, implying that zinc is the one which most likely will undergo oxidation. And copper is the one which most likely will undergo reduction. Okay, so then we come here. Reaction at cathode. You have to know that the reaction at cathode is reduction. So this is our cathode. And this is our anode. That's how we make use of the table. So the question is, what reaction occurs at cathode? You have to know that in terms of ions, reduction is the change from ions to solid. That's what we call reduction. So in this case, which one is our cathode? Is copper. So under this circumstance, we are going to have copper 2 ions undergoing reduction to copper solid. So under this circumstance, what do we do? You have to look at the number of electrons involved. And the number of electrons involved are determined by the charge we have on the ion. So how many electrons? 2. And they come here. Then comes this question. It says that write half cell reaction at anode. Okay. Yes, I need to emphasize that when you look at table 4B, the one which comes first is the anode. And the one which comes later is the cathode. During our times, when we are still at the same level, we used to say that A comes before C, just to recall very fast so that we don't forget. So this is anode, this is cathode. Now, this question wants reaction at anode. And reaction at anode involves zinc. And we need to know that a reaction at anode is oxidation. So in terms of positive ions, oxidation is the increase in the charge or the change from solid to ions. So we are having zinc. So what are we having here? We are going to have the zinc solid here, being oxidized to zinc ions. And the charge we have here tells us how many electrons are involved. And the 2 plus implies 2 electrons. Yeah, then we come to this question. It says that consider part X. So this is X. And the question says, name the part. So what is X? X is salt bridge. Okay. And then comes the next question. It says, name the 2 functions of part X. So what are the 2 functions of the salt bridge? Okay. Okay, the first part is very clearly indicated here. What does it do? It completes the circuit. Because without it, there will be a gap here. So there won't be continuous flow of ions. So that's the first function. It completes the circuit. So what is the second function of the salt bridge? The second function is that it maintains electrical neutrality. So by allowing ions to move across, it maintains the electrical neutrality between the 2 half cells. Yeah, then we come to this question. It says, name any 3 compounds used to form part X and explain the choice of the compounds. Yeah, the salt bridge. What are the compounds which we can use to make the salt bridge? And why do we choose those compounds? Okay. Yeah, the compounds we use, we can, example, we can use potassium chloride. We can use ammonium chloride or potassium nitrate. Okay. Yes, the question is, why these compounds? What's the reason for use or for the choice of these compounds? The reason is that these are electrolytes, but they are inert. Inert means they do not react with the electrolytes in the half cells. Yeah, then we come to next question. It says, write the cell notation of the cell above. Okay. Yeah, what is a cell notation? Actually, a cell notation is a statement which shows the arrangement of the cell without the picture. So it shows you how the cell is typically arranged, but without drawing the picture. So in this case, to have the cell notation, we need to have the half cells. Yeah, we say that zinc is the anode, and this is the reaction which took place at zinc electrode. Zinc was oxidized to zinc ions plus 2 electrons. Okay. Then the reaction at copper electrode, copper 2 ions became reduced to give you copper solid. So our cell notation involves this. It is arranged in such a way that this side we put anode and this side we put cathode. So it's very easy to remember that A comes before C. So which one is anode? Is this reaction at zinc. So what do we do? You write zinc solid, which represents the electrode. Then you say slash. This one represents phase change. This is solid. Now we are going to ions. And the ions are here. They are zinc ions. Okay. We can put aqueous. Then from here, we are going to the salt bridge, indicated by that double slash. Then from here, you are done with A. So we are going to C, the cathode. At the cathode side, our copper ions come, and they're aqueous. And we indicate this one, which means phase change. This is aqueous. We are going to solid. And the solid is copper solid, which is the electrode. So what you have here is the cell notation of that cell above. Yeah, then we come to this question. It says that write the net reaction or resultant reaction taking place in the cell above. So what's the net reaction in this case? Okay, net reaction is the summation of reaction at anode and reaction at cathode. Okay, let us look at here. What reaction took place at anode? It is zinc, which was oxidized, to give you that. Okay, what reaction took place at cathode? It is copper 2 ions, taking up 2 electrons, giving you copper solid. Okay, so the summation of these two is what we call net reaction. So what do we do here? We add them. We have zinc solid, okay, plus copper 2 ions. As for the electrons, they are on both sides and they are equal, so we cancel them out. This one gives us what? Zinc ions plus copper solid. Yeah, this is what we have as the net reaction. It is recommended that when you do that, you cross out the working such that the examiner can clearly see that this is the net, to avoid being mistaken for this. Yeah, then we come to this question. It says that calculate the potential difference of the cell at standard conditions. Okay. So, how do we do this? Here, the best approach is to quote the formula. It says that E naught, not meaning standard, cell is equal to E naught cathode minus E naught anode. Okay. Yeah. So the question is, what is E naught cathode? You need to know which one is cathode. Remember, we said the cathode is copper. And when you check from the table 4b, the answer is 0.34 volts. Okay. Then next, you go ahead and look at E naught anode. And we saw that our zinc is the anode. Okay. And what value do we have from the table? It is 0.76 volts. Okay. So what do? We substitute in there. So we are going to say E naught cell is equal to E naught cathode, which is 0.34 minus, oh, we forgot that this one is negative. So it's minus, so which is negative 0.76 volts. So from there, what do? We go ahead and substitute. So we are having E naught cell is equal to E cathode, and our cathode is 0.34 minus E naught anode, which is negative 0.76, giving us this 1.10 volts. You have to know that this is the voltage taken at standard conditions. Then we come to this question. It says that name the standard conditions applicable to the cell above. What are the standard conditions applicable here? Okay, one condition is that the concentration of the electrolyte should be 1 mole per cubic decimeter. And the second condition is that the temperature should be 25 degrees Celsius. Then we come to this question. It says that on the diagram above, indicate the direction of flow of electrons by use of arrows. Okay? Yes, how the electrons flows. Okay, this is what you have to know. That what we have here as the salt bridge, it's only ions which move, positive and negative ions. So when it comes to electrons, it is in the external circuit where they appear. And how do they move? Okay, the movement is easy to remember. It's from anode to cathode. We used to say from A to C. A coming before C alphabetically. So if this is our anode and this is our cathode, it implies that electrons are going to be moving in this manner. Then we come to this question. It says that state what will happen to the voltmeter reading when concentration of 1, zinc ions increase, 2, copper ions increase. Okay, how do we answer these questions? Okay, here you need to know the half reaction. For the zinc, this is what we saw. We saw that the zinc solid became oxidized to zinc ions plus 2 electrons. Okay. Now I need you to understand here we borrow knowledge from equilibrium. So in other words, what are we doing? We are increasing zinc ions. And the question is, in terms of equilibrium, which direction is going to be favored? When you increase a reactant, it's the reverse direction which is favored. And every time reverse is favored, the implication is that voltmeter reading will decrease. So here answer will be decrease. Okay, let us look at copper. So when you increase copper ions, what will happen? Yes, like for zinc, we need to look at the half reaction. This was reduction, so it's going to be copper 2 ions, taking up 2 electrons to become copper solid. Okay? So, in other words, we are increasing the concentration of what? Of copper ions. What direction is favored? Remember, these are reactants. When you increase the reactants, what happens? Forward is favored. And if forward is favored, it means that voltmeter reading will increase. So the answer here is increase. And with that, I would like to thank you for your time. The channel is PSSB, Physical Sciences Silver Bullet, with me, Richard, here. We appreciate your time. We urge you to subscribe, to comment, to like, to share. Yes, we believe we are simply the best. Stay in touch. See you next time. Bye-bye.